Okay, welcome to our examples videos for 2.1, where we're going to go through a couple of the homework problems from section 2.1 to help us make sense of this idea of finding relative minimums or relative maximums using the first derivative. And we're actually going to start with number 6, even though it's the last problem in your homework, just because the only reason why it's last is because it's an applied problem, but it's a relatively straightforward example. So that's why I wanted to start with this one. So we're given a function, a of t is equal to 0.0265 t cubed minus 0.444 t squared plus 1.749 t plus 7.91. And this represents the amount in billions of dollars invested by large oil companies in exploring for new reserves t years after 1995. So t represents years past 1995. And you'll notice that we're only paying attention for t values in between 0 and 10, which really boils down to we're looking at the years 1995 to 2005. And then it wants me to find the relative extreme points and then to sketch the graph. Well, if I want to find the relative extreme points, what tool am I going to use to help me? I'm going to use the derivative. So if you remember, for that step-by-step process we came up with in my concepts video, is first thing I'm going to do is I'm going to find the derivative, which this is just a nice simple polynomial, so I can use the power rule, and I'm going to get 0.0795 t squared, that's 0.0265 multiplied by 3, minus 0.888, which of course is 444 multiplied by 2, plus 1.749. The 7.91 goes away because it was a constant. There's my derivative. Well, now what? What do I do with that derivative? Well, I'm going to use the derivative to find the critical points by setting this equal to 0. I'm going to set that derivative equal to 0 in order to find the critical points. Now what? I solve for those critical points. Well, how do I solve something like this? Here I have a quadratic function set equal to 0. How do I find roots of a quadratic function? I can either factor, but this factoring is going to be really ugly because it's all these big decimals. So instead, I can just use the quadratic formula. Quadratic formula is negative b plus or minus b squared minus 4ac all over 2a. Well, in our case, this is my a value, this is my b value, and this is my c value. What does that give me? That gives me negative b, but b in our case is already negative because of this sign right there. So I get positive 0.888 plus or minus the square root of negative 0.888 squared minus 4 times 0.0795 times c, 1.749, all over 2 times 0.0795. Okay, throw that into your calculator, and you get the following t values. You get t is approximately, I'm using approximately because you do have to round. You get t is equal to 8.6166, and t is approximately 2.55321. So I'm able to find my critical points, and these represent spots on the graph where I could potentially have a local minimum or a local maximum, or we also use the word relative, right? A relative minimum or a relative maximum. So how do I decide whether they represent relative minimums or relative maximums? Remember, we don't have a graph yet. What we're going to try and do by the end of this is be able to graph it ourselves. Instead, I'll use the first derivative test. And to do that, remember, I'm going to use a number line. Now, of course, we know that I don't actually need the arrows on either side because in this case, I have a limited domain, right? I know I'm starting at 0 and I'm ending at 10. So I only have to worry about stuff in between 0 and 10. But both of my critical points are inside this interval. So here's 2.55 and here's 8.6. So I'm rounding even more. So I have my number line. What does the first derivative test tell me to do? It tells me to pick numbers in between these critical points and then test them. So in this first interval, I can pick the number 1. It doesn't have to be exactly in the middle. It just has to be somewhere in between. Same thing with this one. Between 2.55 and 8.6, I could pick like 5. You could also pick 3. You could pick 4. You could pick 6, 7. Do yourself a favor, though, and pick a nice, easy whole number. And then in this last interval, I could pick the number 9. What am I going to do with these numbers in between? I'm going to plug them into my first derivative. I want to know what the derivative is at 1, what the derivative is at 5, and what the derivative is at 9. So what does this look like? Let's see. So that's what it looks like plugged into my function. If I plug these into my calculator, I get 0.9405 for the derivative at 1. I get negative 0.7035 for the derivative at 5. And I get 0.1965 for the derivative at 9. But these numbers, they're these ugly decimals. The only thing I really care about is whether or not they're greater than 0 or less than 0. So in this interval from 0 to 2.55, my derivative is positive because I checked a point in that interval and the derivative was positive. For the second interval, in between my two critical points, I checked 5 and I got a derivative that was negative. And then in that last interval, after 8.6, the derivative was positive again. So knowing that, I can kind of paint a picture of my function. I can start to get a good picture of what my function looks like. It's increasing before this critical point of 2.55, and then it switches to decreasing because the derivative is negative. Right? It's increasing in that first interval because the derivative is positive, and now the derivative is negative, so it's decreasing. And then it switches back to increasing after I get to that critical point of 8.6. So with that knowledge, what can we say? We can say A of t, what's happening at 2.55? We have a relative maximum at t, sorry, not x, t equals 2.55. And if we wanted to know what it actually was, you can just plug it into the function. So in my case, I get 9.92225, which I got by just plugging in 2.55, and I actually used the whole thing, so 321. Plug that into my function, I get 9.92225. What about at 8.6? Since I'm going from negative to positive, I have a relative minimum. And I know this minimum value as well. It's 6.96858, which of course I got from just plugging the number into my original function. And there's my conclusion. I have a relative maximum at t equals 2.55, and then I have a relative minimum at t equals 8.6166. And I found that out by using the first derivative. So now if it wants me to graph this, well, of course, I'm going to be starting at 0 and ending at 10. In the function, what am I looking for? I'm looking for at 2.5, or around 2.5, right? 2.5, of course, is just rounded. At around 2.5, I'm going to have a maximum. And then what's happening at 8.6, around 8.6, I should see a minimum. So my graph should look something like that. Okay, let's look at another problem. Okay, the next one I want to look at is number 4. So this is just no application here. It's just a pure math problem. Find the relative extreme points of this function if they exist. And then we'll go ahead and try and sketch the graph. So my function here is negative 3 plus x to the 4/5. And there's a very specific reason why I chose to go through this one, and hopefully you'll see in just a little bit. Question number 5 is also a little tricky, but that just requires quotient rule. So it gives you a chance to practice quotient rule for number 5. What's going on in number 4? Well, let's go through those same steps we went through in the last one, and the same ones we talked about in a concept video. So first, what do I want to do is I want to find the derivative of the function. Derivative of negative 3 is just 0 plus, and then x to the 4/5, I can just use power rule. And I get 4/5 x to the negative 1/5. What do I do with that derivative? I set it equal to 0. Well, where does this equal to 0? Well, we have to be a little bit careful here Because if you have a negative exponent, what does that actually mean? That actually means that that x is in the denominator and being raised to the 1/5 power. So if I look at this function right here and set equal to 0, where is this equal to 0? It turns out this is never equal to 0. Because take a look at that numerator. The numerator is constant. The numerator is always 4. So this function is never equal to 0. So does that mean that this function has no critical points? Well, we also have to remember that c is a critical point if the derivative is equal to 0, or what's my other possibility? If the derivative is undefined. So since I didn't find any normal critical points where the derivative is 0, could I look for spots where the derivative is undefined? What does that mean I'm going to be looking at? That means I'm going to be looking at, are there any spots where the denominator is equal to 0? So let's focus on that over here. Do I have any spots where 5x to the 1/5 will equal to 0? Because if that's true, if the denominator ends up equaling 0, then your value is undefined. Well, the 5, I can divide both sides by 5, and I just get x to the 1/5 is equal to 0 divided by 5 is still 0. So it just boils down to that power function right there, x to the 1/5. Where is x to the 1/5 going to be equal to 0? You can just raise everything to the 5th power. What's 0 to the 5th power? 0. So if I tried to plug in 0 to this function, I'm going to get an undefined value. And hopefully, and maybe you guys already saw that a while ago, but that means that, and technically this is step 3, we do have a critical point. My critical point here is x equals 0, because that's where the derivative is undefined. So all that's left is for me to test this critical point to see whether it's a local minimum or local maximum. And this is going to be a little bit easier than the last one because I only have the one critical point to test. So that means I can pick points on either side. There's no in between here because I only have the one critical point. So I'm really just testing each interval or each side of my critical point, because this represents an interval right here and then this represents an interval over here. So I can pick any point on either side. I'm just going to pick -1 and +1. What am I going to do with these values? I'm going to plug them into the derivative. So I'm going to find f prime of -1 and f prime of +1. F prime was just this 4/5 x to the -1/5, but I'm plugging in -1 now. So I get -1 to the -1/5. I can rewrite this to help make a little more sense of it. 4 over 5 times -1 to the 1/5. What are you doing if you raise something to the 1/5 power? You're really just taking the 5th root. So I'm taking the 5th root of -1. What's the 5th root of -1? It's an odd root, so this isn't undefined. I just get -1 back. And so I get 4 times 5 times -1. And so therefore I get 4 over -5. The value doesn't matter. The only thing that matters is whether it's negative or positive. And so we can see here, this ends up being negative, ends up being less than 0. I have a negative value on this side of my critical point. Okay, now let's plug in +1. 4/5 to the +1 of -1/5. I don't have to be as picky with this one because I'm working with +1. +1 to any power is still just +1. So I get just +4/5, which, once again, the only important thing is whether it's positive or negative, and in this case, it's positive. Therefore, what's happening after my critical point? My derivative is now positive. So now we know what the derivative is doing. Let's translate that into what the function is doing. Since the derivative is negative, that means I'm decreasing before the critical point, and then I'm increasing after the critical point. What type of critical point is 0? It's a relative minimum. So f of x has a relative minimum at x equals 0. And you can easily figure out what the corresponding y value is there, right? How low it actually goes by plugging into the function. So in our case, I can do that real quick. You get f of 0 is equal to -3 plus 0 to the 4/5, Well, that's just -3. So there's your relative minimum. Your relative minimum is -3, and it's happening at x equals 0. So if I want to sketch the graph, what am I looking for? I'm looking for a point at 0, -3. That's a minimum. And it actually looks something like this. Notice how instead of being smooth at that critical point, I have an angle, which is why the derivative is undefined there. And there's my graph. Okay, good luck with the rest of the homework. And if you have questions, feel free to reach out and send me an email. And I'll see you in the next video.